And the reason I wanted to start with this commercial is because I'm going to be talking about a special kind of infrastructure. Infrastructure that is very much on the bleeding edge, and in particular, infrastructure that was created for computer scientists who design new systems, new exascale systems, new operating systems, virtualization, do performance variability, investigate topics like energy efficiency, and you can't really design new batch schedulers by submitting jobs to batch schedulers. You need a system that is, in a way, special, that is very sturdy, that allows you to do things, interact with the system at a very deep level, which normal production systems don't allow. Normal production systems provide a very narrow interface that's relatively easy to use, but there is a limit to the knobs you can turn on that instrument, right? There's a limit to that. And I'm going to benefit by my lesson here and turn off that closed caption. Okay, so in a sense, the system I'm going to talk about, Chameleon, is like the kind of car that the snowplow driver needs to drive to the snowplow. But sometimes we all need to do something that is not mainstream, right? Sometimes we all need to drive to the snowplow. It's an early flight or an emergency, and we need to drive through the snowy road, right? This is what happens in science when you design instruments for a new branch of science, for new upcoming topics that have not been solved yet. And that's when you build scientific instruments, and that's when you develop them differently than the status quo. And that's the kind of scientific instruments that I'm going to be talking about today. So in the case of Chameleon, yes, it's built for computer scientists, but it also is built for any emergent topic in science. So we support computer scientists, yes, we also support domain scientists who are not afraid to venture into the less tested waters and who also have the need to build something new. And I'll illustrate that later on with some examples. So first of all, talking about test beds as scientific instruments, those are essentially scientific instruments in infrastructure. So research infrastructure is a tool for computational experimentation because we can envision any sorts of instruments, but in order to actually learn something, we can envision any kind of experiments, but in order to actually learn something, we need to be able to deploy what we envision somewhere, to manage it, to monitor it, and measure things about it, right? And ultimately test our hypothesis, right? So that is the function performed of a scientific instrument. If we don't have it, we have the brightest ideas, we can't really test them. We can't really measure them, we can't compare them, can't quantify anything about them. And if you think about different scientific instruments, they fall roughly in two kinds, right? One is a sort of exploratory instrument. You do something, you enact experiment in that instrument, and then you measure things about, right? So tokamaks, for example, you induce a plasma pulse, you measure the properties of the plasma pulse. There's a different class of experiments that are primarily observatory instruments, like telescopes, for example. You don't go move this planet a little bit to the left, move this one to the right, and now we observe, right? We just observe what is there. We don't interact with the universe, we just look at it. Some of them, that makes the observation function, in a sense, simpler, right? Because you skip this whole interaction bit. And I'm going to give two examples of instruments in infrastructure, right? One of them is more of an exploratory instrument, and the other one is more of an observatory instrument. They are both connected, but in a sense, focusing on observation allows us to skip a lot of complexity, right? So we implement a different trade-off, allows us to skip a lot of complexity that we don't always need. And then I'll discuss about how those instruments can be scaled, and most importantly, how they can be adapted. So in other words, what knobs can we turn on an instrument to explore something else, right? So in a telescope, for example, point the telescope at a different area of the sky in order to explore different things. You can adapt the optics, right? You can zoom in, zoom out, for example, to explore different things. Or you can take the data from a telescope array and combine this data to get a combined, stitched up picture of the sky. All right, so let's talk about the first instrument. Some of you probably have heard about this. It's called Chameleon. It's an edge-to-cloud testbed. Started out as a cloud testbed. It's a data center-focused infrastructure that allows computer scientists explore the kinds of things that I was talking about: performance variability, energy efficiency, design new systems. And for that, they need access deeply to the machines, right? So they need access at the same level, roughly speaking, or in as much as we can make it possible, as if they had those machines on their desktop, right? They need to be able to change the firmware, they need to be able to change the operating system, boot from a custom kernel, change the BIOS, maybe. They, of course, need root permission, they need high level of privilege in order to implement it all. So in Chameleon, most of the system is configured at bare metal. So bare metal reconfiguration allows you to do all those things I just described, but a small part of the system is configurable via virtual machines. Why? Because they allow us to implement a better price-performance trade-off, so to speak. If you want to have isolated access, right, because if you're doing performance variability experiment, you need isolated access, but you can't have somebody interfering with your experiment. You have to, for bare metal access, you have to allocate one whole node. But for a class or another type of research, you might be able to get by with just a slice of a node, and you tie that slice to a virtual machine, and you get isolated environment in that virtual machine that nobody else interacts with, but that means that you can deploy several virtual machines to a node. So chameleons like to change. We named the system because it implements a very deep change. It allows investigators to reconfigure the system deeply. For a testbed for computer science research, we also had to satisfy two other conditions. One is scale, and the other one is diversity. So diversity first, so we support all sorts of different architectures, and you'll see that better on the next slide, but we also support all sorts of accelerators from FPGAs and GPUs through different memory solutions, through different networking solutions that support network programmability. And we then try to have as many of each as possible. Of course, we're limited by the budget, but this is partly also why the KVM cloud is there, where you can support many, many different virtual machines if you need to experiment at scale. Now, the system that we use to program this infrastructure is based on OpenStack, which is a mainstream cloud computing infrastructure. And then we added into that some special sauce, which adapts it to our use case, right? And that includes network stitching, that includes support for various scientific features like access via federated identity, so you can log in with your own credentials, and various other things. And then we also use the system to promote digital artifact sharing, to promote sharing of digitally represented experiments among our community. So Chameleon has been in existence, the project itself has been in existence for over 10 years now. It just recently got renewed for another 4 years. But the system was made available in July 2015. So we celebrated our ninth birthday last year. So over this time, the system has served over 11,000 users, working on more than 1,000 of unique research and education projects in computer science, and also supported emergent research for emergent application science research. And of course, the measure of the system is not really how many users it served, and how many projects it served, but what that community accomplished, right? So scientific instruments are enablers for people's science. So to answer that question, Chameleon was used in the publication of over 700 papers that we were able to track. Not everybody always remembers to acknowledge the infrastructure in their papers, so there are probably quite a lot of papers that we were not able to track. But hundreds of publications were achieved on Chameleon. So a little closer view of the Chameleon hardware. So we've got various different generations of Intel architectures. We've got also AMD nodes. And then recently we invested in disaggregated hardware, that's GigaIO. We've got both GigaIO and Liquid, both with Intel and AMD architectures. So investigators can experiment with changing the relationships between memory and various accelerators that are tied to a node. We've got all sorts of different generations of GPUs from A100s. We should have H100s available soon, to RTXs, to gaming GPUs, which are extremely popular for educational projects. We've got FPGAs with support for that, all sorts of different storage solutions, Corsa switches for programmable networking, and we're always trying to have the best interconnects that support the most experiments. So this is now supported at two sites, at Chi at the University of Chicago and Chi at TAC. And with this new phase of Chameleon, of course, NCAR is joining us as a third site. Hopefully, we will be able to purchase some hardware for NCAR very soon. So NCAR is not really a new addition to Chameleon, because Jeanette here has been operating a very exciting Chameleon volunteer sites. There are other volunteer sites for Chameleon that we have right now at Northwestern, URC, and San Diego Supercomputing Center. That's the via the National Research Platform. And I'm going to be in San Diego actually next week for that reason. So in addition to those investment in data centers, and by the way, TAC and University of Chicago are connected via a 100G link, soon to be 200G. So we've got many interesting networking experiments with large flow. So that is very important to us. And we also partner with the Fabric testbed, which provides core network reconfigurability. So in addition to those data center investments, we also have something called Chi at Edge. This is an edge testbed. So our users were working with various edge projects for a while, and we decided to make that part of the testbed so that they can experiment better. More about that later. So all of this, like I mentioned, is packaged with something called Chi in a Box. And Chi in a Box is just simply takes OpenStack packages with the additions that we made so that others can deploy Chameleon easily. And this is why we have volunteer sites, because others decided to deploy Chameleon, make it easy. We've got independent sites. One of them is created in collaboration with the ARA project. They pretty much took Chameleon infrastructure and decided to configure their own testbed with Chameleon infrastructure. Quite a few of them are volunteer sites, and we're right now working with the Open Cloud testbed with Florida International University. We might actually have another volunteer site at Florida International University before the month is over, with some GPUs, which are much requested by our users. But effectively, Chi in a Box packages both the Chameleon infrastructure and its operational models, allows for the addition of those sites. So this is roughly the hardware that we have and how it's configured. Now, as a user, when you come to the system, what do you see? So first of all, when you're a user, you start with some sort of experimental hypothesis. Now you need to validate that hypothesis, so you look for resources that you can use to validate it. if you're experimenting with machine learning, which most of our users have been doing lately, you're looking for GPUs, right? So we've got a resource discovery system that is both fine-grained and automated in order to keep it up to date. And in as much as possible, we roll a new version whenever the system changes for reproducibility purposes. So now you come to the system, you identify those GPUs, but as often as not, or rather more often than not, you find that they are not available. So the standard crowd usage model, when you go to AWS, when you say, I want to deploy a virtual machine on demand, might not work simply because there are not enough GPUs to go around. Even in Amazon, I'm told you have to wait these days because it's just so popular. So in addition to deal with that, we introduced advanced reservations. So you can come to the system, the GPUs are not available when you come, but you can look at our availability calendar, you can see that a GPU becomes available in a few days or in a week. It's going to depend on the type that you're looking for. We've got 40 RTXs, but just a few A100s, right? So then you can make an advanced reservation for that, and that GPU is going to be there for you for sure when you're showing your demo or teaching your class or whatever it is that you're doing. So once you allocate those resources, once you get a hold of those resources, you'll want to reconfigure them. And like I said, we support bare metal reconfiguration, which just simply means that we will deploy it or re-image the node for you. And on KVM, we will deploy the virtual machine for you. And on edge devices, on Raspberry Pis and Nanos and smaller devices like that, we do reconfiguration by deploying a container, right? And more about that later. We have an image catalog, so you don't have to always configure images from scratch. That said, you can deploy an image and configure it, and then you can snapshot it, so that later on, when you come back, you can start boot from that snapshotted image. We support network stitching and orchestration. Orchestration allows you to deploy complex constructs like virtual clusters. So all those three things, identifying resources, allocating them, and configuring the environment, are available via federated identity authentications. You can log in with your NCAR credentials, don't have to create Chameleon account, and you can access them via GUI, via command line interfaces, or we also support a programmatic interface to the testbed, which is the most powerful interface to the testbed. And it's also powerful because it allows you to write a program on how to create your experimental environment, give it to somebody else, and they execute it and repeat your actions exactly. And that somebody else could be you a year from now when you forgot how to set up your experiment. And then once you're there, of course, you can run your experiment and then analyze and present the results and go back to square one and design the next experiments. Okay, and lest we forget, Chameleon is not just a testbed, it's not just the infrastructure operated in some ways, it's also a community of users. And over time, I made a collage of various pictures of our users presenting their work at conferences, giving demos, working in their labs on various things. And because Jeanette is here, I did have to include a few pictures of the India CC, including the infamous picture from the team in Indonesia that was working during a power outage. So a lot of fun war stories, there. Okay, so we have, and by the way, if you want to read some of those war stories, we have a blog, and every month we profile one of the user experiments on Chameleon. So if you want to see how the users use the system and what research they work on, that's the best way to find that out, right? They talk about how they set up their experiments. So we've got shared infrastructure, that's great, right? That means that you should never lack for resources if we have them. If we can support your experiment, we will. And over time, our users came up with all sorts of very interesting requirements. What can we do with that shared system? So once we have that, once we have some infrastructure that is common to people, we could maybe stretch and work on shared experimental methodology, on taking that community that Chameleon developed and make it easier for them to share experimentation. And one example of how we can make that easier is practical reproducibility. So practical reproducibility is just simply making experiments that are shareable enough that they could be used as a mainstream way of scientific exploration. So right now, when I want to explore science, I generally go to a place like ACL Digital Library, and I look for papers, who else published in that space, right? But I don't go and replay their experiments because the experiments, generally speaking, right now are not ready for it. But what if I could go to a place like ACM Digital Library, and instead of finding people's papers, looking for their papers, I could look for their experiments, and then I could click on that experiment and I could reenact it. I could replay it. And what if I did that, I could change it. I could change their data analysis. Maybe they presented the worst case, and I'm interested in the average case or the other way around, right? So I could change their analysis, but I could also add to their experimentation. I could drop my algorithm and test it side by side with their algorithm. Or if I had a repository like this and could look for experiments, maybe it wouldn't be just the results I'm looking for. Maybe I would be looking for the methodology they used. Right? Methodology is a result in itself. Maybe I could look for different methods of data analysis that they used. And if I could do all this, maybe I could take their experiments and use it in my next class that I'm teaching and assign aspects of this as a homework, right? If this could all be made easy, as it could be if you have shared infrastructure, I could share more effectively. So what do we right now have? What makes me think that we are very close to doing that? Well, first of all, we have an open platform. We have Chameleon. Chameleon is not the only one. I mentioned the Fabric testbed. There's another testbed that is in some respects similar to Chameleon called Cloud Lab. There are 4 wireless testbeds funded under the NSF Power Project. So there are a lot of computer science testbeds where people could find the resources that they are looking for. But secondly, we noticed that over time, Chameleon users produced thousands of disk images. Remember I said you could create a configuration, snapshot it, and then later on somebody can start from that configuration and repeat your experiment easily. So they produced 1,000 images, orchestration templates. If you have a complex experiment configuration, orchestration template helps you deploy it, and other artifacts like Jupyter notebooks, right, and data and things like that. So we already have them. So they already could be used to replay experiments. What is missing? So we already talked about shared hardware. We have that. But what is missing is really end-to-end packaging. So attaching those experiments, disk images and orchestration templates and all of those things, those digital artifacts that users produced, to the papers and to the results and making them findable, right? So a repository in which users could find them, right? And though we have shared hardware, not everybody has access. So for that, in Chameleon, we provide something called Chameleon Day Pass, which allows investigators to give people access for reproducibility purposes. For the end-to-end packages, we provide Jupyter integration and a way for investigators to deploy their experiments or to render their experiments as literate programming exercises. And we provide Provi, which is an experiment repository, which is the sort of ACL digital library equivalent that I just described. And we've got some initial insights from Provi. I started the project 5 years ago, and of course, at the beginning, it was going very slowly, but increasingly more and more people are contributing reproducible experiments to Provi, and increasingly more and more people are replaying it. And we're working very actively with various reproducibility initiatives to make that possible, right? So one idea is right now, reproducibility initiatives, so artifact evaluation initiatives tied to various conferences. They have reviewers who review artifacts and sign off on them, and people get badges, and then nothing happens. Those artifacts are there, but they are not advertised. Nobody's encouraged to replay them. So one way to organize community around this is gather them all up in one place, and organize educational initiatives, for example, that will provide the demand side of the reproducibility supply. So we're working with many reproducibility initiatives at this point to make that possible, and also with various educational initiatives to teach how to reproduce experiments, for example, or how to package them for reproducibility. So now I wanted to circle back and also provide a segue into this other instrument that I wanted to talk about, and talk a little bit about Edge. So Chameleon started as a cloud testbed, right? Data center-based testbed, but over time our users started doing experiments with sensors, like biometric sensors, for example, with federated learning, with network traffic fingerprinting, right? If I open my refrigerator, it generates a packet gets sent on the network, right? Can I reverse engineer from the packets what happened in the room, right? So things like that. But they were only able to explore that via simulation, which is not a bad look. It's not a good look for an experimental testbed if the only thing you can do is explore things via simulation. So we started working on integrating edge devices into Chameleon. And a lot of feedback from our users was, we just wanted to work like Chameleon, but soon people pointed out, well, we also want to be able to add IoT peripherals to those edge devices, right? So edge devices, Raspberry Pis, we want to be able to add cameras to them. Those devices are not server class, so they don't have IPMI. So bare metal reconfiguration is out. How are we going to reconfigure them? And lastly, those devices can't just stay in the data center. They can't stay in the machine room, because the whole point of attaching them to peripherals is that I have a camera that is pointing at something, that is maybe recognizing wildlife. I have a microphone that is doing soundscaping in a forest, and I need that Raspberry Pi to process the feedback from those sensors, right? That's why it's supposed to be there. It doesn't do me any good in the machine room. So out of those insights, we created an infrastructure that supports reconfiguration via containers, right? So that's what I said at the beginning. Provides a framework for adding IoT peripherals, right? So cameras, humidity sensors, temperature sensors, what have you. And also supports the bring your own device model, right? So bring your own device. In other words, our users said, we have Raspberry Pis, they are not expensive, they are cheap. What we would like you to do is give us a way to add those devices to Chameleon, so I can securely share them with my collaborators, right? So not just I deploy stuff on them, my collaborators deploy stuff on them, and so that I can control, right, who can access this device or not, right? Not necessarily accessible to all Chameleon users, right? So that's what we developed for those users. Now, as we did that, and as we did experiments with that, a colleague of mine next door at University of Chicago, who investigates as a big name in broadband and access networks, Nick Feimster, if anybody is part of the broadband community here, came up and said, could we use those devices to implement broadband monitoring? Right, so he said, well, it would be very useful if we could, because then we could see if different neighborhoods across the country have equal access to broadband. And broadband these days is like, basic infrastructure. You can't really do much without good internet access. And then he said also we could answer a bunch of technical questions. What happens in conditions of oversubscriptions, for example? And lastly, we could answer monitoring questions, like what are the fair assumptions to make about broadband when we build new systems? So he said, you're doing those Raspberry Pis. Can you do them for us? Can you create an instrument like this that we will deploy Raspberry Pis across neighborhoods nationwide and measure broadband? And in the end, this turned out to be a yes and no answer. The yes part was, yes, we had a fantastic exploratory instrument in Keahey, but the no part was he was deploying them in neighborhoods where people didn't really have much technical savvy. So turning those devices on couldn't be what computer scientists do. It had to be as easy as turning on an iPhone, right? So we had to give him something that says, plug this into your router and it's going to work, right? So we changed that exploratory instrument into an observatory instrument by taking out some of the complexity that is connected to the exploratory part, diminishing the function. So this is roughly what it looks like, right? If you participate in the broadband monitoring, we ship you a box like this. In the box, there's a Raspberry Pi that you connect to your router, you connect it to the power, and we got 1,000 of those about 18 months ago. And we started the project. So a quick word on how this instrument is implemented. So first, of course, we had to do something to manage those 1,000 devices, deployed 1,000 devices remotely without physical access and such that it would scale. And we developed a system based on OpenBalena, which allows us to do that. We developed dashboards that monitor the health of devices and allow us to drill down on each and every one of 1,000 of them. This is very different than having 1,000 nodes in a data center. 1,000 nodes in a data center is homogeneous infrastructure. This one, by virtue of geolocation, by virtue of the fact that each device is in a different networking and security context and differently geolocated, those are pretty much heterogeneous devices. So I won't dive into details. I probably don't have time to discuss it, though. Please do talk to me afterwards if you're interested. It's a hairy challenge to just manage those devices. Now, how do we give users access to those devices? Well, like I said earlier, users can reconfigure those devices, but by deploying a container. That provides additional isolation encapsulation layer on the infrastructure and makes the user's code more secure, right? And the device also more secure from the user with that code, who brings that code, who could be potentially a malicious user. So we've got a system very reminiscent of OpenStack. Right? It doesn't have the OpenStack interfaces for this iteration of Keahey, but essentially it deploys containers, kind of like OpenStack will deploy virtual machines or reconfigure things on the bare metal for you. So that means that the user can deploy whatever measurement they want in those devices, right? So there isn't just one measurement, one way to measure broadband. Different people have different ways of measuring broadband for different applications. You measure it differently in urban areas, you measure it differently in rural areas, you measure it differently if it's associated with a special application. Now those tests, those broadband tests, they generate data, and they send this data to a highly available infrastructure that originally was running in commercial clouds before we found out how much that costs, and moved it, and currently it's running, it's hosted at Argonne National Lab, will soon be moved to TAC. But it generates, the short here is that it generates data and it processes it. Okay, so now we have an instrument, a scientific instrument, and the question now is, how do we turn the knobs on that instrument? So in other words, how can users customize this instrument to investigate different phenomena? So one way, I already said at the beginning, it's like with any other scientific instrument, right? You can investigate different domain, right? With a telescope, you point at this area of the sky, that area of the sky. With the devices, you can deploy it in this neighborhood, you can deploy it in that neighborhood, you can deploy it for some amount of time. Then we can collect the devices from the people who deploy it in a different neighborhood, right, and run tests. Another way to customize this instrument is instead of measuring broadband, we could measure other things. We could, instead of plugging it into people's routers, we could plug a camera into the device and do image recognition. We can plug air quality sensors into the device and measure air quality, temperature, pressure, any kind of peripheral that you can think of. Another way to do that is adapt the sensing abilities of the instrument by developing different applications. So for example, I already said there are many different ways of measuring broadband, right? I can run my broadband measurement tests, but another group had a different idea and different maybe types of things that they are interested in. They measure broadband differently. They create their own container, they deploy it on the same device, right? My container runs at one time slot, their container runs at a different time slot. We all get different data out of this. And lastly, we can aggregate data differently, right? So we can have an air quality deployment, for example, that is doing federated learning, right, on the devices. That's what one of my students did last summer. And then you don't aggregate the data by simply putting it together and putting it in a database. You create a model that stitches those federated learning models. And of course, lastly, scientists can, once you have the data, scientists can ask different questions of the data. So let me go through all those knobs in how we did it with Floto, right? Floto, this instrument that deploys 1,000 devices nationwide. So first of all, we deployed PIs in various different neighborhoods, and some of those are large deployments. Got a large deployment in Chicago, in Milwaukee, and San Rafael. Those are typically deployments connected to, well, they're really connected to both policy questions and technical questions about broadband. And then we have smaller deployments. One of them is at Marion County, and one of them is in Beaver Island. We've got also others at various university campuses. We have run several different measurement applications on those deployments. So one of them is Netrix. This is back to Nick Feimster, my colleague next door at University of Chicago. That's the package that he supports. But there are many others. Measurements Lab, Measurement Swiss Army Knives. It's a very nice general purpose package. But places like Radar Toolkit, for example, they measure the suitability of broadband for telehealth applications specifically. So they're not interested, good broadband, bad broadband. They're interested, will telehealth applications run on this, right? And there are others. Over time, this deployments and these measurements produced a data set of 13 million data points, last time I checked at any rate, that spanned 17 different providers nationwide and went across multiple technologies, right? So we've got fiber, we've got wireless, we've got cellular, we've got all sorts of things. And it's publicly available. Now, just like with those papers, it's not about how many devices were deployed and what users you had and what applications. It's about what they produced, what insight was gained from that scientific instrument, right? In the case of Chameleon, I was talking about 700 papers because, of course, Chameleon has been in existence for a while. Here, we just got the devices themselves 18 months, so figure in the time to program things and the time to deploy things and the time to then start collecting the data. We've been collecting the data at speed for less than a year at this point. But it has been already useful in two cases. So one, the deployment in Marion County demonstrated that about a third of sampled households were below the federal threshold for broadband. And on Beaver Island, we were able to challenge the FCC broadband maps, which led to reassessment of broadband for the whole island. So this is a way in which the scientific instrument can make real difference in people's lives. And of course, we've got multiple groups working on technical results from this, in particular comparing IPv4 versus IPv6 over broadband, but those are longer investigations, and it takes a time to write a paper and submit it and have it reviewed and accepted or rejected. So we don't have yet papers because there just simply hasn't been enough time. We do, however, have ideas on how to extend this instrument further. And the next step we would like to be to measure rural broadband. Rural broadband is going to be a different use case for us, among other reasons, because we're not going to be measuring round-trip latency. We're going to be measuring point-to-point latency. And for that, we need fine-grained latency measurements. So not NTP. We're going to be putting GPS on the devices, using that to synchronize clocks. We're also going to be using GPS to put those devices and keep track of them when we put them on mobile mobile vehicles, because of course rural broadband, there aren't that many places where we can install those devices. So we had a student kind of exploring some of this and are working on that. Another project, which was done in collaboration with AG and team by a summer student, sought to combine the 3D printed weather stations, which are operated by microcontrollers, with our Raspberry Pis via LoRaWAN, right? So the idea being that you can deploy them. They are extremely power efficient, more power efficient by a factor of something like 5 than a Raspberry Pi, but they can collect data. The Raspberry Pis can collect data via LoRaWAN and process that data. And again, we had a student who was doing that work last summer. And lastly, an example work that we did with marine biologists at Florida International University, where we helped them instrument buoys with a lot of different sensors, and then collect the information from those sensors centrally so that we can work on that. And then here's an example of, and that's a Chi-Edge project. So this is not the observational instrument, this is the exploratory instrument back again, of an educational project where students build their own autonomous vehicles, build their own self-driving cars. Those self-driving cars can be bought from Amazon for about $100. They're connected to a Raspberry Pi, and you can instrument that Raspberry Pi to add it to Chameleon, and then you can write an edge-to-cloud Jupyter notebook that allows you to train and program those cars ultimately and run experiments in self-driving from them. And there are many, many other projects from which you see some pictures here with various different groups that we're working on. And here we're adapting this instrument by adding the different IoT sensors, by developing new applications that we're deploying in containers over the Raspberry Pis. And for the most part, we're collecting the data, though the federated learning project that I alluded to before is, of course, also one of them. And this is really all I have. And so I just wanted to leave you with one parting remark. And I don't know if anybody read the abstract, but in the abstract, I borrowed a quote from David Patterson, who said, "For better or worse, benchmarks shape a field." So he wrote an article, a short article, in which he said, well, of course you have to have benchmarks because they provide a focus, they provide a common denominator that allows us to compare various approaches. And if we don't have such common denominator, then we can't tell which approach is better, this is better or that is better. And he goes on in this article to make the case that if there are good benchmarks for a field, that field is vibrant, and there's an ongoing debate that creates the results that are actually sought and useful. And so something to, and then, of course, when such benchmark is not available, then discussion starts flagging, right? So something to think about when we look at systems being in the post-Moore's law era, look at systems being evaluated by benchmarks tied to the Moore's law era, right? They are no longer really that well applicable, right? And so that's the point here. But what I did is paraphrase that to say, for better or worse, scientific instruments shape a field. Because again, I'm sort of circling back to what I said at the beginning. You can imagine and think of unlimited set of experiments, but the ones that we can actually do are the ones that we have a scientific instrument for. Scientific instrument that allows us to deploy things and observe them and measure them and then ultimately reason about them, right? So scientific instruments create this common denominator, which means that all of us have new scientific problems, and therefore all of us in one way or another are building scientific instruments, right? In other words, we're all snowplow drivers now. That's all I have. Hey.
Questions in the audience or online? Okay. Dave has one.
Back to your practical reproducibility.
Okay, they're using the real mics. So
All right, so for practical reproducibility, how did you define reproducibility in the context of Chameleon? Like there's in computing bit for bit, what's the degree of, do you consider reproducible?
Yeah, so actually, I think the current definition, so the way I define reproducibility in the context of Chameleon is the ability to repeat the experiment that somebody else did, right? So, and from the perspective of practical reproducibility, this is kind of what we're particularly interested in, to allow you to repeat somebody's experiment relatively quickly and relatively faithfully to what they did, right? And this is different, of course, than reproducibility, which sometimes has also been called replicability, when you're repeating a certain scientific process, but completely differently, right? So from the perspective of a practical application, right? So practical reproducibility, we're actually looking for practical applications of reproducibility. From the perspective of practical applications, I want to play with science. I want to have a hands-on feel for science and develop a more intuitive feel for this argument. This is probably the most useful, right? Because the idea there is to give you as immediate as possible way of reenacting an experiment and teaching with it and all those other things.
So there's no guarantees of identical hardware, identical software stacks, or what do you get when you rerun the experiment? Does it specify all of those components? Or?
So what you get in Trovi artifacts typically is a Jupyter notebook, though it doesn't have to be a Jupyter notebook, right? You when you come to Trovi these days, you get, originally you were getting Jupyter notebook because everybody was standardizing on Jupyter and we got caught up in the excitement. But these days you get a GitHub repository, right? You get access to resources on Chameleon, and for Trovi experiments, resources on Chameleon, maybe something like Fabric or ultimately, hopefully, something like Jetstream, is what you normally package the experiment on, right? That's a big advantage of experimenting on shared infrastructure is that people don't need to look for hardware or make some special arrangements to get access to the same hardware that you used, right? And then you get packaging of the experimental environment that they created. And that packaging inside it typically also includes the code that was used to run the experiment, right? So let's say your experiment consisted of running a benchmark. You get an image with everything installed on it, including that benchmark, right? Then you get some instructions or README or maybe a script that runs your experiment. Then you get your data analysis, right? Typically these days, actually tied to Jupyter Notebook, shows you some sort of graph and some sort of trend, right? We encourage the investigators to be very precise about the stopping conditions for reproducibility, right? So what does it mean to reproduce the paper, right? Like students often look at, well, my graph doesn't look like this graph,
Right.
you know? And at the reproducibility workshop that we did last supercomputing, for example, Thorsten Hoffler gave a very good keynote, and he pointed out there were problems reproducing his paper when reviewers weren't getting the same graph that he did, right? But that's because they were producing it on a different hardware that had a bigger cache, you know, and they didn't get out of cache when he got out of cache.
Right.
So it looked different, right?
Right.
So, you get you get the same hardware, you get the same packaging, you get, hopefully, in as much as possible, everything that you need to get to reproduce it.
Any other questions in the audience?
Yeah. Are you using like any other infrastructure as code tools to help with provisioning and making sure things are consistent outside of containers?
Am I using?
Infrastructure as code tools like Terraform, Ansible?
Yes.
Okay.
Yes, absolutely. So Terraform, of course, works with OpenStack. So it's one of the orchestration methods that we support. In fact, we're thinking about dropping support for Heat, supporting Terraform exclusively. Some users prefer to use Ansible or some other scripting, like custom scripting method. We, take the approach that this should all be possible. Some users prefer to write a program in Python G, right?
Yep.
Or use Jupyter for, Python G in Jupyter.
Nice, so it's flexible, basically whatever the
Yes.
user's comfortable with.
Whatever the user is
Awesome.
comfortable with. Otherwise, and there are other tools like GUIs is another one that somehow, I don't know, some people are promoting it or if it's gaining popularity, but we've got definitely users who's doing that, right? And if we were to restrict those methods, I think it would be too difficult for community. It would be too difficult to uptake things.
Cheetahbox also makes heavy use of Ansible to configure it as well, so.
Yeah.
Thanks.
I mean, call Ansible for configuring the system itself, for configuring
yeah,
Chameleon. And users, of course, don't see that, right? So
Yeah.
users use Ansible to configure their experiments
That's right.
in different contexts.
Any other questions in the audience? Otherwise, I have one with reproducibility and atmospheric research. We're not really the best at building reproducible experiments, I'd say, all the time. So just, asking in terms of your catalog of experiments and workflows that you're putting together, including digital object identifiers to those packages, and have the researchers actually cited those in peer-reviewed publications?
Yeah. So Toby is integrated with Zenodo.
Okay.
So you can get DOI from Zenodo for those purposes.
Have you thought about does Chameleon itself have a DOI?
Chameleon, so Chameleon various papers have DOIs.
Okay.
But the project itself, it's like a testbed itself.
It's not like a physical something you can
Yeah.
cite, because there's a research coordination network project here on PIDs for instruments. So, you can cite instruments and helps it with provenance, chain of data and all that stuff. And then it would help with formal citations and papers where you're counting.
Yeah, it's an interesting idea. I used to be a co-editor and I co-founded a journal called Software X, which was publishing software as a scientific instrument, right? And the idea, we're talking about infrastructure scientific instruments, but software itself too can be considered one. And there we were definitely creating DOIs for various different software packages, and there were, interesting questions about as those software packages evolve over time, do they deserve a new DOI, or how do they change or should DOIs? So there's a lot of interesting work that goes on that is related to publishing digital artifacts or infrastructure artifacts. And while we didn't create a DOI for Chameleon, maybe it will come in some ways.
Anything else? Anything online?
Nothing on.
If not, let's thank Kate again. Thank you.